In this video, we're going to talk about the rate equation. And then we're going to show you what the rate constant is and how you can determine the units of the rate constant and the units of rate, and go over some AS rates in order as well. And we'll also talk about how you can determine orders to place into the rate equation. So first of all, we're going to go over AS rates of reaction. So if you look here, you would have done your first year of A levels and you would have looked at rate and said it's changing property over time. So the three types of change in property. The first one is the change in concentration over time. And I just want to show you here the units of concentration and the unit of time, because what we do is we get the units of rate from whatever we use to calculate. So in this case, we're using concentration, so it's moles per decimeter cubed per second. Now, I want that second to be the numerator. I want it to be part of the rate units. So rate equals those units. So if I want to move it up, it's like timesing it by -1. So if you ever have a unit at the bottom that's divided by like that and you want to turn it into the main units for the product of the equation, you have to times whatever's the denominator by -1. And you end up with moles per decimeter cubed, which you get from here, seconds minus 1, because we times the S by -1. We do exactly the same with the second type. The second type is when you look at the change in volume over time. Centimetres cubed seconds. So it would be centimetres cubed seconds minus 1. We then look at this again and we look at the mass change. Sometimes you will lose mass, for example, if you're losing a gas through an experiment. And so we do rate equals mass over time. Okay, and that would be grams second, so grams per second. Now, the one we'll use all the time though is concentration. So we're going to concentrate on that one and then look at the rate equation itself. So the rate equation is equal to your rate constant. So here is your rate constant K. Okay, and that rate constant K is times by your concentrations, which I've highlighted in orange here. And if you ever see a molecule or a letter or something like that in square brackets, it's telling you it's a concentration. So it's really, really important. So these square brackets denote its concentration. And then we go to these M and these N. Now they're the orders that you have to find out. And in this video, we're going to talk about how do you find out those orders. But before we do so, we're going to talk about how do you find out the concentrations to even calculate rate. And there are two methods we're going to concentrate on. One is colorimetry. Okay, so the first one using a colorimeter, which you may have used in biology. Okay, it just takes, in simple terms, a source of light and then something that selects the wavelength of light. So, for example, 540 nanometers or something like that. It selects it, and then it passes that selected wavelength of light through your solution, whatever your solution is. So what you can actually do during an experiment is take out solution from the experiment, test it in the colorimeter, place that solution back, test it again 5 minutes later, okay, and you can determine the concentrations using this method. Now we do it with something called a cuvette. So this is normally a rectangular shape, and you can see here your solution will go inside the cuvette, okay, and it has a frosted front and back of the cuvette. And you can see it's frosted blue part here. That doesn't let light go out, okay, from two of the sides, which means the light must travel through. And you can see the light now going through and goes through our solution there. Okay, so it doesn't escape from the front or the back. And from there, we then have a detector at the end which detects the absorbance, for example, 0.77 as an absorbance. And we know how much of that selected wavelength your solution has absorbed. Now there's something called the Beer-Lambert law, which is absorbance equal a constant times concentration times path length. You notice there's concentration there and absorbance. Now this isn't actually in your course, but it's important because you can see the link between absorbance and concentration. And the path length is just the length here. So normally that is about 1 centimetres cubed. So if that's 1 centimetres cubed, and that goes up there, okay, we can ignore path length. And we can say, because there's a constant there, that absorbance is actually proportional to concentration. So if we know the absorbance, what that basically means is we can work out the concentration. But how would we do that? Okay, how do we work out the absorbance from the concentration? Well, we would do it doing something called a calibration curve. So the calibration curve you've got here shows absorbance on my y-axis, and then down here it's concentration. So a scientist, for example, has literally just made up different concentrations of a certain chemical, for example, the chemical you were going to do or use in your reaction or create in your reaction, okay, or use up. And then they have placed it into a colorimeter, managed to get all the absorbances of all those different solutions and plot a graph. Now, if I'm going to really tune this down and take this to what you would do if you're monitoring a actual reaction to link to the rate equation, these concentrations would be of your reactants, because in the rate equation, we only look at the reactants. Okay, so what you then do is you can take that graph and you, for example, tested one of your solutions. It was 1.2 in absorbance at 540 nanometers, okay, which means that it's 38 milligrams per centimeters cubed. And you can then place that into your rate equation. And this is one way in which you can find out the concentrations to place in your rate equation. The next method for finding the concentrations for either a time concentration graph or for your rate equation, essentially, is to use a reaction where a colour change happens. And you can measure the length of time it takes for that colour change to happen. Now, the most famous one is an iodine clock reaction. So data can be obtained from separate experiments, and each experiment will use a different concentration of one of the reactants. So you will change it gradually. And we'll go through examples of what you do to use the rate equation and find out K in our exam style questions video that follows this. Now, the iodine clock is basically a solution. We've got it here and we'll show you in a second. And it's an example of which is this one, where we've got hydrogen peroxide plus our iodide ions plus an acid. In this case, it was sulfuric acid. You create iodine, so we can see iodine here, and you also add starch. So the starch, if you do biology, you'll be used to this. The starch will react with the iodine and create a blue-black colour. Okay, but we also add thiosulfate. And thiosulfate will then react with the iodine that's produced and turn it back into iodide ions. Those iodide ions are colourless. So basically this reaction will stay colourless until the thiosulfate has been used up. And then when it's used up, it goes black. So let's have a look at that. Okay, so all I'm doing now is adding the hydrogen peroxide, and you can see very quickly thiosulfate is going to be used up and it turns that blue-black colour. So it goes colourless to blue-black. So all we do to measure the rate for this, okay, remember we know the concentrations because we knew the concentrations of each one of the reactants, okay, when we started. But if we want to measure the rate for this, because it's a colour change, and any colour change one you can do exactly the same way, you can use rate equals 1 over time, and that will give you your rate for these kind of reactions as well. Now that we know how to look at or create time versus concentration graphs, let's look at what some of them look like. Okay, so these are all based on continuous monitoring, so measuring that concentration over time. Okay, so here we have our first one, and you can see that this gradient here, okay, going down, it's very characteristic. There's nothing else like it. So the concentration is reducing slowly over time of this reactant. Now that is a zero order reactant. Okay, and this will all make sense in a minute. Zero means that you would raise this to power 0. Okay, but we'll go over that in a second. The next one is our A, but this time it's a first order reactant. And you can see we've got this nice curve, okay? So it's nice decreasing curve. Now, that curve over time will create your first order reactant. Again, that will be raised to power 1. We'll then go for the last one. And again, you've got an even steeper, kind of deeper curve, which is second order. And you only have to do 0, first, and second order throughout. And I think of this as like you're pushing down on the line. So if I push down the line, it's going to get deeper, and I push down the line, it's going to get even deeper. And you've got these 3 graphs for 0, first, and second order. But let's concentrate on 0 and pass it over to the middle. So I said in the rate equation, remember we're only doing a reaction with a reactant A for now to keep it simple. So your reactant is A, okay? You know from this graph that it's 0, okay? So you raise that to power 0. If you raise it to power 0, you don't have to write A in the rate equation. Rate will just be equal to K, okay? So then we go for the first order reactant. We're raising that to power 1. Now if we're raising it to power 1, we don't need to write the 1. Okay, so rate is going to equal K to the times the concentration of A. We then go to second order, okay, and the second order one is to 2. So we've got our 3 equations. For 0 order, recognising this is really important, and you will be asked this in exam style questions, so make sure you remember these. Rate is equal to K. This one, rate equals to K times the concentration of A, and this one, rate equals K times the concentration of A squared. So if you see this type of graphs, concentration time graphs, you've got to make sure you know all of them. We're now going to show you the concentration versus rate graphs, which you have to recognise and remember. So we've got a flat line here for a 0 order reactant with the concentration on the x-axis and the rate on the y. We then have a straight line from the origin with a proportional relationship for a first order reactant. For a second order reactant, we have this positive curve. Now let's go through each one in turn. And what you think, what is the relationship between the concentration and the rate? Well, as I increase the concentration, the rate stays exactly the same. And that is your justification for why something is a 0 order reactant with this data or with the graphs. That means you raise your reactant to the order and power 0, which means you don't include it in the rate equation. And that makes sense because inside the rate equation, the constant times the concentrations changes the rate. Well, if this doesn't change the rate, I shouldn't include it. So with concentration increasing, the rate does not change. We then go to first order reactants. So it passes through the origin. An example is if the concentration doubles, the rate doubles because of this proportional relationship. Okay, and it's really, really characteristic in terms of memorizing it. Now that means we raise the reactant to order 1, power 1, which means it is just literally the concentration of A. And that makes sense because it affects the rate. We then go to second, and we see this positive relationship again, this curve. And what happens there is that if the concentration doubles, the rate is multiplied by the square of that change, or the square of the decrease. So if we have the concentration is times by 2, the rate will be times by 4. If the concentration is times by 3, the rate will times by 9, because it's the square of that change, okay? Really important. If you're not sure whether this is a second order, you can square the concentration on the graph. And you can see here the concentration is squared, and we've got a nice straight line graph. So if you're doing practicals, that's one way of confirming you've got a second order reactant. Because sometimes when you're writing lines of best fit, it can be hard to determine. So put it into the rate equation, and we've got it squared. So let's now take this and summarize all of them. So we've got our time concentration graphs here, and we've got this line which imagine you're pushing down on it, pushing down, okay? And then we've got our rate concentration graphs. This time, no effect, proportional, and then it's the square of the change. We're now going to go over the units of the rate constant, because that changes depending on what rate equation you have in front of you. But first of all, we need to know the units of rate. Remember the units of rate if we're changing concentration in moles per decimeter cubed seconds to the -1. Let's put that over there to remind ourselves, and then let's look at our first equation. Now where A is 0 order, rate will be equal to K. Now if that means that rate is equal to K, let's look at what units we would get. So that means if the units, and we'll write this down here, if the units are moles, dm seconds -1, and we're that for rate, okay, that means we're that for K because the same units. So K's units are going to be moles dm minus 3 seconds minus 1, because rate is equals to K. Same units as you have for rate. Now what have we got first order? So first order will be rate equals K times the concentration of A. But if you divide by A over, you will equal K. So if we know what the units of these are, we can work out what the unit of K is. So let's do that. So we know that the units of rate are going to be moles dm minus 3 seconds minus 1. Okay, so we've got that. And then we divide that, and we know what the units of A are. Well, the units of A is a concentration, so it's just moles per decimeter. And then all we do is we cancel out the moles per decimeter because it is both the numerator and the denominator. So we cancel that out completely. That means the units of K, if we go over here, are going to be equal to seconds minus 1. So that is if you have this kind of equation for a rate equation. We will go over more complex types when we go through exam style questions. Now, what about if it's second order? So second order, we've done this. And now let's look at what that does in terms of units. So we start off with rate again, and we're going moles dm minus 3 seconds minus 1. That's our rate. And then we do our concentrations. Now, the important thing is that's squared. And because that's squared, it's like squaring this thing here. But I'm not actually going to square it like that. I'm going to square it like this. Okay, so there we go. So we've got there. So there we go. Right. Now, if that's the case, I'm going to cancel it out this time by using my trusty board rubber. And I'm going to get rid of this one. Okay, and get rid of this one. I just cancelled that out. Okay, so let's just get rid of that. There we go. Right, so we've cancelled those two out. Now, the next thing is, if you're going to raise this up to the numerator, it's like timesing it by minus 1. And we need to raise it up to get rid of this division, okay? So this is like timesing it by minus 1. So that means, if I times that by minus 1, that becomes moles minus 1 decimeter 3, because I'm timesing the minus 3 by minus 1. I'm timesing the mole on its own by minus 1. And that gets rid of our division and leaves us with these units. Now we're left with those units. Now that's perfect. That would give you the correct answer. Okay. But what they like you to do, so a preferred one, so I'll do this in a different colour because it's the preferred, is you put your positive one first. So the proper exam answer would be decimeters 3, so it picks out the decimeter 3, mole minus 1, and then I would do the seconds minus 1. And that is how you do the units for 3 simple rate equations. And like I say, we'll move on to more complex rate equations in a later video. We're now going to determine the orders by data. So here's some data, and here's some rate of reaction. So it's telling you the concentrations of A, B, and C. Remember, we're only looking at the reactants. It's the rate equation. We only look at the reactants. So here's the details for 0, first, and second order, saying for 0 order, rate does not change. First order, rate increases proportionally as you change concentration. Second order, the rate increases by the square of the change in concentration. I'm going to start off with reactant A. We've times it by 2, and as you can see, the rate has not changed. It's stayed at 0.1. So therefore, that must be a 0 order reactant because the rate has not changed. That means our rate equation is going to be rate equals K, because I'm not including A in my rate equation. We then move to B. We've doubled B, and we're going to compare A to C, because that has 2 of the reactants exactly the same, and just 1 has changed. So 0.1 has gone to 0.2. You can see as I've doubled B, I've doubled the rate of reaction. If that's the case, that's a proportional relationship, which means it's first order reactant, which means it's included in my rate equation. We then move to C. If you look at C, I have tripled C. Because I've tripled C, I then look at what I've done to the rate of reaction. That's times by 9. Now, 9 is the square of 3. 3 times 3 is 9. Okay, so this means the rate has increased by the square of the change in concentration. If it's done that, that means it must be included in the rate equation, and it must be second order. So that is how you use data to find out the different orders and then make up your rate equation, and from there you can calculate the rate constant. Now also what you can now do is determine the overall order of the reaction. Now that's a really simple calculation. It is simply adding all the orders together to produce the overall order. So for this reaction, the overall order is 3. So we're now going to look at, if you know the rate equation and you're given some changes in concentration, how can you use those orders to determine what the overall change in rate will be? So how will the rate change if the concentration of B is doubled? Well, B is a first order reactant, and therefore the concentration of B being doubled means that the rate will also double because of that proportional relationship. Concentration of C is triple. Well, C is a second order reactant. Because it's a second order reactant, it will change by the rate will change by the square of the change in concentration. Well, the change in concentration is times 3, so the square of that is 9. So that means the rate will times by 9. We then combine the two together, and that's the important thing. So here we triple both. Well, if we triple both, that means that we're going to have 3 times change for B, because it's a first order reactant, and then there'll be a 9 times change, because we've already done that here, for C. Now all you do is times those numbers together, which means rate is times by 27. And you'll need to do this often when you're looking at questions, so it's a good one to get used to. We're now going to reverse this and see if we can get a rate equation from knowing the changes in rate from the changes in concentration. So the first one is, in this reaction, D, E, and F. So if we look, when the D is doubled, the rate is unchanged. Well, that tells me that this is going to be a 0 order. We then go to here, when E is quadrupled, the rate increases by 16 times. Well, 16 is the square of 4. So that means this is going to be second order. Then when F is halved, the rate is halved. Well, that is a proportional relationship. Okay, so that means I'm going to put that down as first. So we've got 0, second, and first. All we have to do that is then apply that to our rate equation. So rate is equal to K. In this case, we've got D. We know D is 0, so we don't include it in the rate equation. E is second. And there we go. And then F is first. So F is first. So there you have your rate equation that is created from knowing the rate changes from concentration changes. In the last part of this video, we're going to find out whether this is a first order reaction or second or 0 from this graph. Now, as you can see from the title, this is a first order reactant, but I want to show you how you can tell that from this graph. Now, this is time versus concentration. Really important here, it says times 10 to the minus 3 as well. That's really good to look out for because that's often where people make mistakes. And that we'll come into that further when we do the calculations video. But this concentration of Y, you can see it looks like a first order, but how do we actually 100% make sure? We make sure through something called half-lives. So half-lives means I'm going to change the concentration, I'm going to look at the concentration, and I'm going to halve it. And when I halve it, I'm going to put a line where I halve it and go out to this curve. And then I'm going to draw another line down, and then I'm going to measure how long did it take for the concentration to halve. And you have to draw these on graphs. When you get a graph like this, and you want to confirm it's first order, you have to do these half-lives. So the time it takes for the concentration to halve, what is it? And you need at least 2. So there you go, there's another one. I've halved it again, and then I'm going to take my half-life, and then you look here again, I've halved it again. So if you can do 3, do 3, but if you can only do 2, do 2. And that turns out to be 18.5 seconds. Now, because they're constant, then you can say this is a first-order reactant. That's what you're looking for, this constant half-lives. So first Y, in this case, is a first-order reactant. Now, I want to go through some exam tips here as well. This is commonly used to assign orders, so you really do need to get used to it. The half-lives will most likely not be perfectly equal. So if you do this in an exam and they're not perfectly equal, it still is going to be first order. If they're just slightly different, just a tiny bit different, it's still going to be first order. So just as long as they're close to each other, you can say it is first order. But do the graph really carefully. So if you see a graph is given, I want to see these lines absolutely perfect, because you'll get marks for them.